So today the class is divided in half. The first part I will be giving a refresher on basic knowledge that you need to know in order to delve into functional analysis, while later Charlie will be discussing about the knowledge of probability that you need to have in order to face this course. We are putting slides and notes online, so that from slides from previous years and notes, so that you, if anything is not clear after these refreshers, you can check them and see what you didn't get clear. But of course, you can ask questions as soon as you have them today. Okay, so regarding the functional analysis part, we are going to see two objects, Hilbert spaces. We're going to consider concepts of Hilbert spaces and linear operators. And the main reason why we are focusing on these two objects, in particular Hilbert spaces that will be ubiquitous during this course, is that, as Tommy said in the previous classes, one fundamental ingredient of any learning problem is to define a good space of functions where you look for candidate solution of your problem. Okay, and as it turns out, Hilbert spaces are extremely flexible, so they allow you to define and to describe many interesting families of functions that we are going to study. And at the same time, they provide you with enough structure to, and simple enough structure to do optimization, to use linear algebra tools, but also on spaces of functions that can be infinite. And indeed, we are going to review a bit of the kind of operation that you can do on an Hilbert space through linear operators, that you can see them a bit like generalization of the concept of matrix in a finite dimensional space. So let me start by giving you the definition of Hilbert space. H is a Hilbert space if is a vector space equipped with an inner product that I will denote like this, and complete with respect to the norm induced by this inner product. Okay, so I introduced this concept: vector space, inner product, completeness, norm. I will go through all these points in order to refresh what they mean. Now, I'm assuming that all of you have already seen vector spaces, so if you have not, maybe you can check the notes. I'm not going to give all the definitions, but basically these are sets where you can do operation like sums and multiplication by a scalar. In particular, in this course, we are going to consider vector spaces on the real field, but with some, small change. All the things that I'm going to tell you today can be generalized also to the complex case. Anyway, so examples of vector space that you have probably seen are the set of real numbers, or it's a Cartesian product with itself, like Rn. Then you have infinite spaces like L2, the space of all square summable sequences, or space of functions that would be like interesting for us in order to look for a candidate solution to a problem, like the set of square integrable functions on the interval, for instance, 0, 1. But you can have many, the space of continuous functions, 0, 1, or you can make many examples. So these are all vector spaces. Not all of them are Hilbert spaces. We'll see why, what kind of things they do not satisfy of this definition. But anyway, once we have a vector space, we will want to, for instance, do operations and compare elements in the space, since we are looking for a solution that is actually is an element of this, is a vector in this vector space. It will be a function in this vector space. Therefore, we need something to compare them, and inner products are are an extremely good tool to do that. So the definition of inner product is this. Let's assume that we have V a vector space, and we have that this operation, this function that goes from v times v to R is an inner product if must satisfy three conditions. So the first one, it must be symmetric. So v times w is equal to w times v for each v and w in v. Then it must be bilinear. So lambda 1 v1 plus lambda 2 v2 w must be equal to lambda 1 v1 w time plus lambda 2 v2 w. Sorry. For each lambda 1, lambda 2 in R, and for each v1, v2, and w in V. Okay? So it's bilinear because of the symmetry, so we can do that the same thing on both sides of this function. And finally, it needs to be positive semi-definite, which means that the inner product of an element of the vector space with itself must be always greater or equal than 0. And furthermore, it will be 0 if and only if V is the actual 0 element of your vector space. Okay? So this is called the positive definiteness of the inner product. Okay, so examples that you have probably seen for inner products are on R, for instance, the vector product, for instance. So you have x and y elements of Rn, and you can define the inner product between x and y as, you can also write it like this in a sort of matrix notation. And is simply the sum y that goes from 1 to n of xi, yi, where x, I've written it in its coordinate with respect to Rn. Okay? So this is the inner product of, is an example of inner product on Rn. You have probably seen something like this for functions, like the set of square interval functions on 0, 1. We can take two functions here, f and g, and define the inner product of f times g on L2 as the integral between 0 and 1, f of x, g of x in dx. Okay? And this is well defined, and it's actually satisfying all these properties and is an inner product on L2. Well, in this case, I took the simple case of the interval on the real line, but of course, yeah, you can take a much general space, yeah. So, okay, so we have inner products. Now we have among the many properties that inner product have, they also induce always a norm on the space they are keeping. And norms are extremely useful for instance, to measure the relevance in some really hand-wavy sense of different vectors, their length in some sense. Of course, this makes it more intuitively clear in Rn. It becomes less clear when you're starting to consider norms in infinite-dimensional spaces of functions, for instance. But so the definition of a norm, which doesn't require the definition of an inner product, is the following. You take a vector space, V. A norm is a function that goes from V to R, okay, and satisfies, first of all, non-negativity. So the norm of V is greater or equal than 0 for each V in V. And furthermore, we have that the norm of V is actually, so the inequality is strict, the equality holds only if V is actually the 0 element of V. Then we have that a norm must be homogeneous with respect to the field. So lambda V must be equal to the absolute value of lambda times V for each V in V. And of course, lambda in R. And finally, we have the subadditivity. So v plus w must be less or equal than the norm of v plus the norm of w for each v and w in v. Okay? And the point is that you can easily verify that if you take this definition, the definition of this norm, as the square root of the inner product of an element with itself, with respect to an inner product, for instance, the one that we saw there, this one is a norm. And is the norm that is induced by that inner product. Not all norms will be induced by some inner product. That will make the difference between different kind of function spaces. But so the main point of introducing a norm is the fact that norms provide lots of tools to study how sequences of elements in a vector space behave. Of course, we could just use very weaker notions such as that of metric or topology, but since we are always working with Hilbert spaces, so we'll always have an inner product and the norm induced by an inner product, we're going to see what means convergence with respect to a norm. And therefore, let's go with this definition. So we can take a sequence Vn, sequence of elements in our vector space. And we say that Vn converges to V as n goes to infinity, with a certain V, exists a certain V in V, if, well, the norm of Vn minus our target point converges to 0 as n goes to plus infinity. So we are leveraging on the fact that we have a structure of a real field. We know what limits mean in R, and we are using this information to construct convergence, define convergence in the vector space. So we are getting close enough with this sequence to this point, and asymptotically we are converging to that point. So norms allow to do this, and every convergent sequence in a vector space has the following property. For each epsilon you take greater than 0, there exists a number n epsilon, for instance, a natural number, such that for each small n and small m greater than this number epsilon, the n epsilon, we have that Vn minus Vm is smaller than this epsilon. So what this means is that if you take arbitrarily, arbitrarily far elements of this sequence, arbitrarily in the sense that they will be larger than a certain number that you don't necessarily need to know, the two elements, the couple of elements that you take from this sequence will be arbitrarily close one to the other. And basically what this is telling you is that the sequence is slowing down so fast that the distance between two elements far enough in the sequence is getting close to 0, is tending to 0. And this property is called Cauchy. So a sequence that satisfies this property is called Cauchy sequence. Okay. However, it's not always true that this arrow can be inverted. So it's not true that if you take a sequence that satisfies this property, that sequence is Cauchy. And this is actually, strange if you think about that. It means that you have a sequence in your space that is slowing down very fast, up to the point that, any 2 points that you take arbitrarily large can be arbitrarily close one to each other. But this is not converging to a point in your space. And indeed, we won't like this kind of spaces, and we're going to consider Hilbert spaces that are so-called complete. And complete means that for a space that every Cauchy sequence is actually converging to a point in that space. So if we take V a normed vector space, so a vector space with a norm, is complete if every Cauchy sequence is convergent in V. Okay, so we are not taking spaces that have holes in some sense. And indeed, example of complete spaces, the standard example of a complete spaces is R, which actually is by construction complete. Because if you ever seen the way you construct the set of real numbers, is exactly done by taking the set of rational numbers and taking all the Cauchy sequences there, and using the limit of that Cauchy sequence that is not converging as the symbol that you're using for filling the hole in R. For instance, you take a Cauchy sequence that you know that gets close to pi, for instance, so to square root of 2 or something like that, and you add that symbol to your space, and in the end you will get R. So this process of completion, it's usually indicated like this, and so R is the completion of Q. Okay, some less standard example that you can have of a space that, for instance, is not complete, like Q is the set of functions that are continuous on a closed interval, such as this. Because in this case, you can have, you know that the space of continuous functions on a closed interval is contained in L2, and therefore it has an inner product on it. Okay. Now, I will be a bit hand-wavy on the kind of proof showing that C is not complete with respect to the norm induced by this inner product, but bear with me. So I'm going to take this sequence of functions f of n that are done like this. So I have the interval 0, 1. I'm going to take some interval ab, which is constant for all elements in this sequence. So this is a function that is 1 here. And then it has a diagonal slope here and here. It has these two diagonal components. And the only thing that I change as n increases is the steepness of this slope. But this steepness will never get to be vertical. So all these functions are continuous. Therefore, are in C 0, 1. Okay? The only problem is that if you take this sequence, which is of course a sequence in L2, this sequence will converge in L2 in the norm, which we denote like this, norm of L2, will converge to this f bar, which is done like this, which is the step function of the segment AB. Of course, this one is not continuous. So f bar is not in C 0, 1. Okay? So the point here is that we have a sequence which in this space with that norm is convergent, so it's a Cauchy sequence because we know that every convergent sequence is a Cauchy sequence, but this Cauchy sequence is not converging to a point within C. Okay, is it clear? Okay, so the point here is that C is not complete, therefore it is not an example of Hilbert space, like instead L2 on 0, 1 is. The main point is that it's not always true that C, I mean, it's not true in general that C is not complete. You could consider other kind of norms, right? So an example is the one of the infinite norm on the space of continuous function, which is defined as the maximum of the absolute value of f of x with x in the interval. This is a norm. And actually, with respect to this norm, C01 is complete. Okay, and the intuition behind this is the fact that by changing the norm, you're changing the set of the family of sequences that are actually Cauchy or not. And indeed, this sequence is not Cauchy anymore with respect to this norm. Indeed, if you take f of n minus f of m, okay, any two elements in this sequence, you can see that the maximum of the difference, since the support is decreasing at each step, is actually constantly 1. Okay, so this of course will not be a Cauchy sequence, and that's the intuition behind why this space can be complete. You are reducing the number, the set of functions that are the set of sequences that are Cauchy, and that therefore need to converge. Okay, so now we have the definition of a Hilbert space, we can go through it again. We have an inner product. We have the norm induced by the inner product, and we see that this is complete with respect to this norm. And so this space, they all satisfy this kind of condition. And apart from the definition of Hilbert space, apart from the concept of Hilbert space, we will actually use some further property. We will actually ask our Hilbert spaces to have the further property of being separable, and I will tell you in a moment why. So, I guess I will erase this part. So, I guess throughout the course we will always assume, unless specified, that spaces, the Hilbert spaces, are separable. And so the definition is as follows. V is a normed vector space, again. Actually, it's a Hilbert space, we don't care. Okay? And we say that is separable if there exists a set S contained in V such that S is countable, and 2, if we complete S, we get V. Okay? This is exactly the same thing that happens in the case of the real numbers with the rational numbers. So the point of this definition is to tell you that we will work with spaces that can have fancy structures, that they'll be infinite dimensional. The main point is that we will in some sense want to control the kind of size that these spaces have. And the reason this happens, I mean, intuitively, is that there is a skeleton which is countable. And this means that every point in this space can be reached by a sequence in the countable space. So the actual dimension of the space, although infinite, is controlled in some sense by the fact that there is a space that is countable inside. And we will see in the following theorem why, what this actually means. So we have these. So we have as a hypothesis that V is a Hilbert space, and that V is separable is equivalent to say that there exists a sequence Vn of elements in V, which is an orthonormal basis of V. And this means, I can put it like this, but it's countable. Okay? So by requiring separability, we are imposing our Hilbert space to have a countable basis. This is very important when we are going to study linear operators and why we can generalize properties of linear algebra to infinite dimensional spaces. So, orthonormal basis means that you have elements in the basis which are normal, which means that they have norm 1, and that they are orthogonal. So the inner product of Vi times Vj is equal to 0 for each I different from j. Okay, and the point of having an orthonormal basis, what gives you is the fact that for each element, well, I write it here. So an orthonormal basis tells you that for each x in your space, you have a unique representation of that vector, unique decomposition of that vector in terms of the linear combination of the elements of the basis. So in this case, what means that we can write x as the series, here we put plus infinite, of the projection of x over the VIs times the VI. Okay, this is the unique way of writing an element with respect to its basis. And well, we like the fact that this is countable. Okay. So now that we have imposed all our conditions on Hilbert spaces, we can start to think about what we can do, what kind of operation we can do on Hilbert spaces. So if you have any questions on this first part. Okay, so linear operators are the most natural operation that you can do on linear spaces because they maintain the structure of linear space as they operate. So the definition is quite simple. A linear operator that goes from a space V to a space W. I'm assuming throughout that they will always be Hilbert spaces that are separable. Actually, linear operators do not need all these kind of properties, but for simplicity, let's assume that they are always like this. So L is linear if it has the linear property that we have seen before. So L of lambda V1 plus lambda 2 V2 is equal to lambda 1 L V1 lambda 2 L V2. Okay. So as I told you, linear operators are a sort of generalization of what matrices are in the finite dimensional case. Indeed, if you take V and W to be, for instance, Rm and Rn with some m and n, you have that L can be associated to a matrix L with n rows and m columns. Okay? And it's always true that if you take a matrix with n columns and n rows and m columns, it induces a linear operator on your space. And therefore, we can generalize some properties of matrices that we know. For instance, we know that for matrices, we have the transpose of a matrix, which is an element in Rm times n. Okay, and you can define transposes as, defining how you change the elements in the matrix. But of course, you can have a more abstract definition that actually allows us to generalize the concept to that of adjoint of a linear operator in the case of generic infinite spaces. So from the transpose of a matrix, you see that, for instance, if you take vectors like x in Rn and y in Rm, you can define the inner product between x Ly like this, or, well, transpose, or also L transpose of x applied to y. And these two are simply, if you write them in the inner product notation, as x times Ly, which means that it's equal to L transpose x and y. And indeed, the definition of a joint, which is the generalization that we want now, is the following. So L star that goes from W to V is the adjoint of L if for each V in V and W in W, we have that V, well, LVW with respect to the inner product of V, of W, sorry, is equal to the inner product of V times L star W, the inner product on V. Okay? So if an operator, if a linear operator satisfies this property, it is the adjoint of L, and you can show that it always exists and so on. Now, if you have L, well, let me write it there, L that goes from V to the same space, you can define what is called a self-adjoint operator, which is an operator which is equal to its own adjoint. These are self-adjoint and are the generalization of symmetric matrices. Okay, good. So, okay. So before going further, I guess I can introduce also for self-adjoint operators the concept of eigenvectors and eigenvalues. So we have L, a linear operator, which is self-adjoint for simplicity, and V is an eigenvector for L with eigenvalue lambda in R. Okay. If L applied to V is equal to lambda V. So basically, if you apply the linear operator on the vector, you get back the vector but scaled by a certain lambda. Okay. So so before going to the spectral theorem that will allow to generalize concepts such as the decomposition, the eigen decomposition, and then singular value decomposition in the case of linear operators, we need to introduce a class, a specific class of linear operators that are compact operators. You will not really need to know what compact operators are for the class because we will always work basically with compact operator, I guess. So this is just the notion that is needed, the property that is needed in order to then to do linear algebra on our function spaces. So I'm just going to tell you what it is, but you will need to understand it if you don't have this kind of knowledge. So the point is that a linear operator is compact if you take the image of the unitary ball in the space V, and the closure of this object is compact in W. And compact means that if you take any open cover of this set, you can always find the subcover that is finite and still cover the entire object. Okay, so this is the property that we actually do need in order to get to the spectral theorem. So the theorem goes like this. We have a Hilbert space, L that goes from V to V and is self-adjoint and compact. That's why we need it. Okay. The thesis is that there exists n of elements in V and a sequence lambda n of elements in R, which is an orthonormal basis for V, but at the same time is also a set of eigenvectors with these kind of eigenvalues for L. So L of Vn is equal to lambda n Vn for each n. Okay? And this actually implies the following thing, that L can be written in terms of these operators. The summation of n that goes from 1 to infinity of lambda n times Vn composed with Vn star. Vn star is the transpose of Vn, and Vn is the operation that goes from, here I'm writing with some abuse of notation, but the fact that Vn is the metric that goes from R to V and sends an element sigma in sigma Vn, okay, in the scale version of Vn. And you can get, of course, the transpose because these are linear spaces, the adjoint of Vn, and you get two functions and you combine them. So this object, the combination of these two elements, is what is called a rank 1 operator because the image of this operation is a vector space of dimension 1 in your target space. And therefore, yeah, these vectors, they are not only a basis for your space, but they are actually also a way to decompose your linear operator. And then furthermore, we have that the lambda n goes to 0 as n goes to plus infinity. This is true for compact operators. Okay, so this generalizes what you already know for matrices, the fact that you can do the eigendecomposition. And indeed, for a self-adjoint operator, you can write in this way what I've written here in a more compact way. So L is the combination of the following three linear operators, where U goes from V to V, and also sigma goes to V to V. They are designed accordingly, but basically it's the combination of these three linear operators. So you can always take a self-adjoint operator which is compact and expand it like that. And this will be useful because then when we're going to roll out the class, you will be just using this formulation and you're just going to work with this object without thinking too much if you can do that or not, because you know that all the properties that you need in order to do that, they are available. And so as you have this, as you have the eigendecomposition, you can have also the singular value decomposition for generic compact operators, which simply requires to introduce just a bit more of notation, but it's exactly analogous. So you take L that goes from V to W and is compact. And then you have that there exists a sequent Vn, Wn, sigma n of elements in V, in W, and in R. These are orthonormal bases. And we have that L can be written as the linear combination of rank 1 operators that are like this: sigma I, Wi combined with Vi star. Okay, and you can do exactly the same thing as here. So you have L is equal to, okay, this is P sigma Q star with Q and P according to the spaces will be Q from V to V, P from W to W, and sigma that goes from V to W. Okay, so of course there will be the generalization of what are orthonormal matrices. So this will be what are called unitary linear operators, that are operators that go from one space to the space to itself, but they don't change the norm of the vectors. And I guess this is all you will probably need for the class. Yeah.
What is the difference between a self-adjoint compact operator and a Hermitian operator?
Sorry?
What is the difference between a self-adjoint compact operator and a Hermitian operator?
And an Hermitian. So you need, in the case that in which we are now, so using the real field, the point is that an Hermitian has the property basically in this case that is positive semi-definite. So what you have is that if you take V and take the inner product with L applied to V, you have that this is greater or equal than 0 for each V in V, and this is positive semi-definite. And in the case of the real field, it's actually the definition. It's actually equivalent to Hermitian. While for the complex case, it generalizes a bit more. But the point is that you have this, and you can see these. These are required to be self-adjoint. And so Hermitian operators can always be decomposed, can always be seen as, let's call it M times M star. So the operation of a linear operator with its own adjoint. Okay, so it's a self-adjointification in some sense that goes this way. And if you go to the spectral theorem, what is actually characterizing this kind of object is the fact that you not only have that these lambdas, this sequence of lambdas must be in R, but must be in R plus. Okay, that's the difference. And indeed, I mean, if you think about matrices, you have positive semi-definite matrices which are symmetric, but have also the spectrum, which is always non-negative, while symmetric matrices can have real values, but on the spectrum, but it can be negative. That's the. So I guess if you don't have any more questions, Charlie.
Yep. Hello. Okay, so I'm doing the second part on probability theory. So something that we want to study in this class is a theoretical framework for analyzing the performance of learning algorithms. And that is going to rely heavily on probability theory. So the basic setup is this. So a learning algorithm, we're going to treat it as mapping a sample of input-output pairs to a function. And this is the function that you're going to use to make predictions. And the sample we're using a subscript n to indicate that this is a sample of n points. So this is your training set. And what we want to study theoretically is the performance of the algorithm, the error that it commits on the test set and the training set. And for that, we use two concepts. One is the empirical error. Yeah, I can try. Okay. So the empirical error is the average loss on your training set. And V is the loss function. And this could be, for example, like the square loss or the hinge loss, things that were probably mentioned in lecture. All right, the second notion we're going to use is the expected error. Right, sorry. So back to empirical error, we're going to denote that by this function I sub n of f. All right, that's the empirical error of the function f. And then the expected error is going to be very similar, but it's an integral now over the entire space of possible xy pairs with respect to a probability measure on the xy pairs. And just hopefully makes it a little clearer. So our sample is coming from a space that I'll call Z. So the integral is this space over the space Z. All right. So there are two major theoretical concepts that encode sort of what we mean by good performance of a learning algorithm. And one of them is called consistency. And what consistency says is that the expected error of the function that you learn is close to the expected error of the best possible function in your hypothesis class. So f sub n is the function that we learn, and and that's converging to, let's call it f star, is the function with the lowest expected error in the hypothesis class. And consistency is, this is an asymptotic notion, so this is true as in the limit as the number of samples goes to infinity. All right, and I don't think it's a notion that we're going to spend a lot of time on in the course. The one that we really focus on is generalization. And generalization is about the relationship between the empirical error and the expected error of the function that you learn. And it looks somewhat similar. So again, it's asymptotic. It's as the number of sample points goes to infinity, the empirical error converges to the expected error. Okay, so now what we would like to say then is that our learning algorithm generalizes if this is true, and that means that the empirical error is a good proxy for the expected error. And one way of looking at it is that you can analyze your performance on this finite data set by analyzing the expected error, which can turn out to be tractable to look at. All right. So there's also two related notions. One of these, well, I'll just talk about one of them. So something that you'll see is the generalization error. And this is probably the closest one to what you would intuitively expect a measure of the performance of the learning algorithm to be. And this is saying that for a finite number of examples, the empirical error is close to the expected error of the learn function. Okay, and this will be true with some probability. Oops. Which we're going to say is 1 minus delta. All right, so it's giving you a relationship between this upper bound on the difference between empirical and expected error versus the number of training points in your training set. And you want that to be small. Okay. So for the rest of the time here, what I'm going to focus on is generalization. And the full definition is we want to say that that this quantity, the empirical risk, converges to the expected risk in probability. Oops. Okay. So what I'm going to do is try to unpack exactly what this means and start from basic definitions, random variables, and stuff like that. So first of all, the random variable here, there's really, there's several, well, okay. So the randomness really starts with the training set. Okay, you have samples, these XY pairs that are sampled from some distribution. And from that randomness, we have a function of our training set, which is the error at any one of these points. So this is a random variable whose probability distribution is derived from the sample. And then, of course, the mean error is also going to be a random variable whose distribution is derived from the sample. Okay. So a random variable then, we're just going to think of it as being a variable that takes on values in some range. Okay, for example, the reals, and is defined by a probability measure. Oh, sorry. Where's the eraser? Oh, great. Okay, so we're going to have a variable that has values in some range, and the most important part is that it's associated with a probability distribution or a probability measure. The probability measure, what it does is assigns probabilities to sets that are subsets of whatever this range is. Okay, and we'll call that subset an event. And the assumption that we normally make when you're talking about a measure over, say, the pairs that comprise the sample is that they're IID. So you have a collection of random variables, n of them in this case, and what that means is that their joint probability distribution is exactly the product of the marginal distributions and these distributions are all identical. So independence is that the joint factorizes as the product of the distributions, and then the distributions for all of the random variables are identical, is the ID part. Okay, so that's IID. And then the last concept here is the expectation. So the expectation of a random variable is going to be the integral over its range with respect to its probability measure. Okay. So if anybody has questions about that, then I guess let me know. Otherwise, all right, I'm going to move on to how we actually go about proving something like this statement of generalization. And the fundamental problem is that we want to prove something about, we want to bound this probability that the empirical risk deviates from the expected, but we don't actually know what the probability distribution of these random variables is. Okay? And the tool that you can use in this case is called a concentration inequality. And what it gives you is if you have some very limited information about the random variable, such as its mean or bounds on its value, then you can bound the probability of certain events. Usually that the value of the random variable will be greater than some fixed value. You can bound the probability of that event. So I'm going to show maybe the simplest concentration inequality, which is called Markov's inequality. And the information that you have about your random variable in this case is just that it's non-negative. So all of its values are greater than or equal to 0. And the statement is that if I take some constant, some positive constant c, then I can bound the probability that x, this random variable, exceeds c by its expectation divided by c. And that's true whenever, for any non-negative random variable. So the proof is just a couple of steps. So we'll just write out the definition of the expectation. Okay, and all of these values are positive, and so clearly if you take out part of the domain of integration, then the value of that integral is going to be less than when you have the whole domain of integration. Is this still too small for people? Or? Okay. Okay, so we take out part of the domain of integration. And so instead of integrating from 0 to infinity, we go from c to infinity. Sorry. And that value should lower bound the expectation. And all of these values of x from our domain of integration are greater than or equal to c. So if we instead say that instead of x it's just a constant c, then that integral has a value that is less than or equal to the value of this integral. And we can factor out the c. Okay? And then now you just apply the fundamental theorem. Okay. And so what we have on the right-hand side here is just the probability that the value of the random variable exceeds c times c. And so rearranging that gives the inequality. So Markov's inequality is true for any non-negative random variable. Now, another inequality that we're going to end up using is Chebyshev's. And now the random variable is no longer non-negative. It can have negative values. But what we know about it is that it has finite variance. Which is sigma squared. Okay. So what we want to bound now in this case is going to be the deviation between x's value and the value of its expectation. And we'll call that f of x. Okay, so we want to bound this probability of f of x be greater than or equal to c. Now, it turns out for Markov's inequality, you can prove in almost exactly the same way the analogous inequality for any non-negative function of any random variable, meaning it maps the random variable to non-negative values. Okay, so we're going to use that to derive a bound in terms of the variance on this value. And the trick to this one is we can go ahead and apply a monotonic transformation to f and the same transformation to the constant, and then the probability doesn't change. So we can go ahead and say that that probability is equal to this probability. And then applying the Markov's inequality, we get this. And the value, that expectation on top, is exactly the variance of the random variable x. So this is our bound. It's sigma squared over c squared. Okay. So those are two pretty common concentration inequalities. And so that gets us some of the way towards proving that the value of that probability on the inside of the limit is bounded. Now, the limit itself requires that we define convergence in probability. Okay. So I'm going to define convergence and probability, and then we'll combine it with the concentration inequalities to prove something close to that statement, but not quite. So convergence, just regular convergence of a sequence. So these are not random variables. This is just any sequence of numbers or elements in a set or whatever. And you're going to say that, let's see. Let's just say, so the sequence approaches a limit x if for any epsilon, if for any epsilon there's a point in the sequence beyond which, oops, beyond which for any element all of the elements beyond that point are within epsilon of the limit. Okay. And that holds for any epsilon, and when that's true, then you say that the sequence converges to the limit. Now with probability, there's a few ways to define convergence of random variables. You have to deal with the fact that you have a probability distribution now. The definition that we're using here is convergence in probability. And what we'll say is that random variables x sub I converge to a limiting random variable if for any positive epsilon you have this is true. The sequence of probabilities that the random variable deviates from the limit converges to 0. So this is one way to define convergence of random variables to a limit, and that's the definition that we're using in generalization. So generalization is really saying that the empirical risk converges in probability to the expected risk. Yeah.
You're saying this for all epsilon, not for a particular one, right?
Right. Wow. Yeah, right. For all. Okay. So now we can put that together with the inequalities over there to prove something like this, but not quite. It's the weak law of large numbers. And what the weak law of large numbers says is that you have this sequence of random variables of length n. These are IID. And they have a common mean. And variance. We'll define their empirical mean just the same as over there. So it's x bar sub n equals the average of their values. So this empirical mean is also a random variable. And what we want to show then is that it converges to its expectation in probability. So the mean of the random variables converges to the expectation as the length of the sequence goes to infinity. Okay. So this is basically one step, actually. It's going to be just an application of Chebyshev's inequality. And the key fact that we need is that the variance of this random variable is finite, and we want to know its value so we can plug it into Chebyshev. So So let's see. Just writing out what this variance is. I'm just using the definition of the empirical mean. This is the definition of the variance. And expectations are linear, so we'll rewrite it, pushing it inside the sum. And so this here, this value we already know. The expectation of the random variable is just mu. Did I forget a square? Yes. Let's just write it like that. OK. So this value here should just be mu. So we have mu squared. And then this value here, we're going to use the fact that these are independent random variables. And when they're independent, they're uncorrelated. And so any of the off diagonal, if you want, any term here where j is not equal to I is going to be 0. It's just what it means to be uncorrelated. So this turns into just a sum over the expectations of these random variables squared, okay, minus mu squared. And we can rewrite it one more time like this. And to make each one of these the expectation of the random variable squared minus its mean squared. So okay, so this thing on the right is just the definition of the variance of any of the random variables x. And so what you get is the variance of the empirical mean is the variance of the individual elements of the sequence divided by n. Okay, so that's going to be our key fact. So we know that this random variable has finite variance, and we can just apply Chebyshev's inequality then, which is going to say that the probability that it deviates from its mean by more than epsilon is bounded by the variance over epsilon squared, which is equal to sigma squared over n times epsilon squared. Okay. Now the key property, this is true for any element of the sequence, and then the key property is that these converge to 0, which is going to be true because the n's on the bottom here. So as n goes to infinity, this goes to 0. So that's the weak law of large numbers. And it looks a lot like our definition of generalization there. We have the mean of these random variables converging to the expectation. Does anybody see why this does not suffice to prove that the given learning algorithm generalizes? So there's an assumption that does not hold in the case that we're looking at in the class. So the assumption that doesn't hold is that the random variables that we have here, these individual losses, they're not independent. And the reason is that the learned function depends on all of the points simultaneously. So we no longer have independent random variables, so we can't just apply the weak law of large numbers. And I guess later in the semester, we're going to show a way to approach the problem for this particular learning setting. So that should be pretty much it. Do you guys have questions? Okay.